Hi, my name is Harsh. I am open to machine learning research at rephrase.ai, and today we'll be talking about unit style transfer. First, I'll briefly introduce myself, then we'll move on to the agenda of the day. So, I pursued my electrical engineering from IIT Bhopal, Varanasi, India. Then, after that, I went for my master's in robotics at Untitled University. I have mostly been working on understanding how machines learn and how, in context of computer vision, how a particular robot or any kind of machine learning system would perceive and understand a scene. So it's not just learning, but semantic understanding of a scene is what I am most interested in. I have worked at Indian Institute of Science, Bangalore, under Professor R. Venkatesh Babu. Then I have been a student of Year 3 at National Center for Robotic Vision, Adelaide. At CMU, I was mainly a part of Cognitive Assistance Lab under Checo and Friscatani, and right now I'm at Reflex. I love singing, watching and making films. Like that's kind of my hobby, and I think that's what gives me life. Art. My prior work has mostly focused on semantic understanding in different contexts. I started off by understanding images and sketches. After that, I went on to work on development of an end-to-end SLAM systems using deep learning. We were one of the early, our paper was one of the early papers in this particular field. It was like the second or third paper. And SLAM has a problem. I'm not sure if a lot of people have context about it. SLAM is basically the way you enter a world or a building. You are reading a map of the building and you're simultaneously understanding the location with respect to the map that you're making. So SLAM is that problem for robotics. Visual SLAM is when you are having computer vision and sensor and you are creating that map. In SLAM, particularly, I worked on deep learning based SLAMs and geometry based SLAMs. In geometry based SLAM, I was working with Marshall where we were trying to incorporate uncertainty estimation using deep learning and using that as a prior for classical geometry based SLAM methods. My thesis was on developing deep learning systems for blind navigation. Essentially, we were trying to make an indoor Google Maps version for buildings where that application could be used for blind people. Currently, I've been working on generative algorithms for facial and style reconstructions. And I have some experience in RL, not much, but like I have been working on a robotic arm which can be controlled using RL, where we tried incorporating finger-like constraints the way human fingers are designed, and that was under Matt Mason at CMU. Okay, to reach out to me, the best way is send me an email. You can search me on LinkedIn, and I'm mostly active. I would love to interact and talk to everyone. Okay, so now let's go on to the presentation. I'll first briefly introduce rephrase and then we'll move on to unit style transfer. So, rephrase.ai. What do we call rephrase? We generate real human videos from just text as an input. So, essentially, this whole talk that I'm doing, I could make it a rephrase by just entering the script and you will have me speaking this whole, like the whole text that whatever you enter. The process is simple. On our portal, you can just type in your script, choose an AI speaker, select some voice, and the video will be generated. On top of that, you can also animate, add music, customize backgrounds. So essentially, the end product on our portal is a full-fledged professional 4K quality shoot without any kind of camera, green screen removal, actors, nothing. You just have to enter the text and you'll get a video. What are the potential applications of this particular technology? Well, varied. Some to mention would be personalized sales and marketing, edtech content creation, digital marketing, A/B testing. So essentially, you can roll out multiple campaigns because now you don't have to shoot every video. You can have personalized sales and marketing because, for instance, Shahrukh or any kind of brand ambassador could come and say you, hey Suhas, how are you doing? Because he doesn't have to shoot it. You can just get some 5-minute snippet of that person, use our deep learning algorithms for understanding the way he speaks, and his expressions, his tone, his voice, and we can clone it. Definitely, it has ethical constraints, and that's why we have strong ethical policies as well. But this technology, if it comes into existence, has a lot of good pros as well. So hence we are working on it. Cool. This sounds amazing, isn't it? So please visit us at rephrase.ai and sign up for a free demo. And we would love to talk, chat, and interact how we can help you in your businesses and your endeavors. Okay. Let's move on to neural style transfer. Before I delve into the actual presentation, I'll just stop here to say, if anything, think of it as a classroom. If anything is like not making sense, if you are facing issues, please stop me. I'm not sure, I can't see anyone. I cannot really see anyone. You're on a different screen and I'm sharing a different screen. So please stop me and let me know. I can stop and I can give you some context behind whatever I'm saying. And if you feel that a certain topic needs to be covered, well, I have some margin for that as well. I've covered 5 to 10 minutes extra. I've decided 5 to 10 minutes extra and I've prepared the slides for that as well. So if you feel that a certain topic is just completely out of view, we can talk about that. Cool. So let's move on to neural style transfer. Everyone with me till now?
Yeah. If anyone wants to just keep the question in the chat box, please type it here, and maybe just after the talk we can take it in.
Sounds good. So let's move on to neural style transfer. Neural style transfer. Let's break this term into 3 words: neural, style, and transfer. First, let's talk about neural. Everything these days which is cool and popular is neural, deep, convolutional, or some kind of network, right? So here we are doing something related to neuron. Neural essentially refers to neuron, and in our case it will be more like neural networks, which are essentially parametric function approximators. Parametric function approximators, as in it's a function approximator from input to an output, where you have certain parameters which can be trained or learned. Okay, style. What do we mean by style? A style is a typical feature or an attribute. Like I'm having specs, someone is having a beard, someone is fat, someone is thin, someone is robotic, someone speaks in a different accent, someone writes differently, someone has hairstyle. So a style is a typical feature or an attribute of a particular person, thing, object, anything. That's what style means. So here we have different animation styles of a particular cartoon character. Okay, what do we mean by transfer? Transfer is essentially moving, right? You could move things, you could move knowledge, you can move attributes, you can move anything. Now, what do we mean when we combine all these 3 terms? Neurons, neural networks, a typical feature, and transfer. Well, we are essentially moving from one feature space or domain to another with the help of neural networks, which is in general the problem of solving neural network problems. Whenever you solve a neural network problem, you are essentially going from one domain to another. Here specifically, you are moving in terms of a feature space. Hence, the papers you read in neural style transfer will be very closely related to meta-learning, domain adaptation, few-shot learning, transfer learning. No worries if you don't know these terms. They are very similar and have a very strong intersection. When you read these methods, you'll be able to find parallels, and hence I wanted to just mention them. Although we'll be focusing on NST, which is neural style transfer. So a simple example, you have an input image, an input style, and you come up with an output image where the style is taken from the style image and the content is taken from the input image. Right. So this is from a paper which was very recently published, which has a combination of all the methods. I would recommend everyone reading this paper, Neural Style Transfer Review. It has been recently published and it's worth a read because it combines the literature of all the methods in past 10 years or so. Well, it is actually that old. People don't believe that neural style transfer is that old, but yeah, it is that old. Cool. So, what is neural style transfer when you cannot play around with your images? So, I decided to take one of my image and tried, stylizing it using multiple painted images, and I created this using an online tool which is instapainting.com, which is another deployment, you can say, of Gator Sital's method. It uses that algorithm, which almost everyone is using. I went through the teams and people are mostly using that, the TensorFlow tool. Cool. So what's the importance of it? Certainly, you cannot expect researchers to work day in and day out to solve paintings. It's an important concept. It's an important problem, but there should be more to it. Why are we so interested in solving neural style transfer? First of all, we are trying to learn how to represent and disentangle abstract semantic information. Now, what does that even mean? So essentially, in any system, when you want to represent it and fiddle around with it, you need to represent that information in a mathematical form, a vector. We want to learn how to represent semantic and complex relationships as a vector, which is what the power of deep learning is essentially. Secondly, we want to learn how to transfer semantic information from one agent or system to another. Let's say I know painting and you know photography, right? Can we combine the two? Let's say I know how to cook any food and you know how to cook Italian food. Can we combine the two? Can we use that knowledge? There's something that's common. There's something that's different. Can we exchange that knowledge? Right now in a hackathon, someone is a developer, someone is a machine learning engineer, someone is from some other domain, research analyst, consultant. Can we transfer information from one agent to another is what we are interested in. Now, why does that make sense? ML systems right now need so much data to work that you cannot, if I want to train a dog cat classifier, I need 10,000 images of dogs, 10,000 images of cat. Now, if I tell you that, there's another animal that looks like a cat, then I need 10,000 images of that other animal as well. Essentially, we should not be needing that because humans don't need it. We are transferring that knowledge, right? So we are making machine learning systems more reliable, more practicable, and useful. When we deploy such systems where we can transfer semantic information and disentangle representations. And to a certain degree, we are trying to understand at a very minuscule scale how living beings perceive relationships. Maybe there is some kind of a parallel. But now the question is that it's a very common misconception. If you type on Google style transfer, you will typically get examples of just images, right? Now, is this only for visual learners? Think of it in this way. When you talk to a friend, as compared to when you're talking to, let's say, a manager, there are two different forms. There are two different ways in which you are speaking, right? Even there are styles. So moving from a formal conversation to an informal conversation is also style transfer, right? So it is used in movie. Let's take another very weird example when people typically don't imagine style transfer. Robotic manipulation. Let's say you are trying to learn how to hold a pen from a particular person. So there's a style of calligraphy that you want the robot to replicate. That's also style transfer, essentially. There's very less work in these two domains. NLP has a lot, I would say, but it's not very extensive. It's still a budding field. Robotic manipulation, style transfer, I have yet to see a lot of papers on it. I have seen some in 2020 ICRA where they are trying to understand how they should grasp a particular object based on the stiffness. But this is still a very new field of research. But the question remains the same. If you understand style transfer in computer vision or in any system, you can use the mathematical models that you develop in several domains. And that is why this problem is extremely important to us. How do we transfer information from one system to another? Okay, so now, everyone with me till now?
Yes. Yes.
Yes.
Yes.
Yeah. So now, how old is style transfer? You might wonder that last 3-4 years everyone is talking about, not 3-4 years, but 2012 Kritzwitsky et al. Came up with the AlexNet, and since then, deep learning is the de facto way of solving a problem, right? You have an input, you have an output, you throw a network, and then things learn. But this problem is actually very old. Like you transferring some aspect of one image or some feature of one image to another has been there forever. For instance, there's a dark image and there's a light image, and I want to convert the dark image to a light image. Right? It is essentially some kind of pixel correction. I need to add darkness. I need to add brightness. We do that on our screens all the time, almost. What are we doing here? We are having a distribution of RGB pixels that we are trying to manipulate. And finding out a linear approximation or a non-linear approximation to transform these histograms from one space to another is essentially what the whole problem of machine learning is. And histogram matching, these images are from MATLAB. You can have like simple IMist match, just one line code to actually make this happen. So this problem is not new. But what is new is the scope of this problem, because now with the deep learning you can represent such abstract concepts as very high dimensional features, 1024 dimensional features, 4096 dimensional features, and the level of abstraction has increased. And you can transfer a combination of styles. Here we were talking about only, the brightness or the RGB pixel values. Here we are talking about the essence of the picture, the way the strokes have been taken, etc., etc., etc. Things that we as humans, as artists, think about. Hence, deep learning. So it's an old field, but it's still young. Just the way this man is, Cool. So let's move on to the prerequisites. Now, I would love to know this. Oxford Group. It stands for Visual Geometry Group 16. It's a 16-layer architecture by Visual Geometry Group, and the architecture was used for image classification. There was a problem called as ImageNet, which had around 1 million, 10 million images to classify into 10 classes, and VGC16 was the state of the art at that moment. So it's a very standard convolutional neural network which is used for image classification. Right, so essentially a network that is used for image classification. The idea is that once you have trained the network to identify, okay, this is a cat, this is a dog, this is a tiger, this is an elephant. It understands and perceives the basic features. What are the edges? What are how is the texture? How is the color? And stuff like that. It has learned to identify that out of images, and that's where VGC16 content is very famous. GANs. I'll briefly talk about it just before I discuss the method on GAN. Most likely we'll not go through the mathematical formulation of it, but if time permits, we can do that as well. Cool. Okay, so this is a VGC16 architecture actually. It has 16 main layers and 2 FCs. And there's an input which is a 224 cross 224 cross 3 image, which is like height, width, and the number of channels, RGB. And you have 2 layers which are capturing the high level information, and you have multiple layers which are abstracting the knowledge. So as you can see, slowly and steadily we are trying to reduce the size of the information. Now let's see what's happening under the hood. I'll just label the layers L2, L5, L9, L13 and L17, and I'll talk about it later. Why did I label these layers? So let's take an input image. This has been taken from a tutorial on towards data science, by the way. Well, let's take an input image and pass it through a VGC and visualize the feature maps. What is a feature map? A feature map is when this image is paused at every consecutive layer, like the layer 2, what is the output? What does the output look like? At layer 5, what does the output look like? At layer 9, what does the output look like? So, layer 2 features look something like this. Okay. Layer 5 features look something like this. Layer 9 features look something like this. Layer 13 features look something like this. And layer 17 features look something like this. Now, what is so interesting about it? I'll just keep going back and forth so that people can actually see what is happening inside the deep network. Why is the deep network so powerful? What is the magic? You can see that layer 2 is capturing high level information. Edges, frequency, what is the overall structure, and brightness, contrast, things like that. Layer 5 features are more abstract. And as we move on to layer 17, they're just highly abstract, just speckles. That, okay, maybe this corresponds to the back headlights being present. There is, you can't even annotate these features as something. Maybe these are just headlights in a particular pose. But these are extremely abstract features, right? A combination of these features is going to help you in identifying whether it is a car, or it is a truck, or it is a bus, or it is whatever. Now that we understand what the feature maps look like, so I just summarized it over here. Initial layers are basically capturing the high level information like edges, textures, etc. etc. As we move deeper in the network, the information is becoming more and more abstract, and the diversity of features from low level to high level, including your semantic content, is being captured in all these feature maps. And that is why these deep features are so powerful. When you do an edge detection, when you do some hog feature detection, you are capturing one aspect of the image, or maybe two aspects, or maybe 5 aspects of the image. When you have a 16-layer model with 64 filters in each, I don't know how many features are you trying to capture over here. Maybe pose, size, magnification, everything is being captured over here. And hence these features are so powerful. Okay, now that we know about the basic, what is a deep feature essentially, let's move on to style transfer. And I'll tell you why this was so important. Okay, now you have, this is the example that Pranay also talked about in the morning. You have a style image, which is like, I don't remember the name of this painting, but it's a very famous and beautiful painting. And there's an input image, and you pass it through a network, any neural network for now. Let's assume that it's something similar to a G60. Actually, in this paper, they use a G90, which is a 19-layer version of just a G60. So you have these feature maps, and these feature maps are converted into some kind of style representation, which are nothing but covariance matrices of the feature maps. So essentially, you have a feature map here. You club all those feature maps and get a covariance matrix. You combine these two features together and get another covariance matrix, which is slightly bigger in size. You combine all these 3 features and you get a covariance matrix, which is slightly even more bigger because you have more features, and so on. So now, the interesting part about it is that using the features, you can try reconstructing the image. You have when you are trying to find out information, you are trying to filter, and that's the term that's typically used. You have filters in a coordinate. You're trying to filter information. So when you try regenerating the image out of the initial layers, right, the reconstruction is almost perfect. Here's the image that is reconstructed, here's a small patch that is being reconstructed, and it's almost perfect, However, when you do that for the later layers, the reconstruction is really bad. Okay. So that means it's tough to construct something out of abstract information. Yeah, true. Because you can have multiple possible outputs. It's a highly ill-defined problem. Let's look at the style images. Well, certainly this image over here, E, does not look at all like the style image. It's just capturing the texture of it. How are the features related? How are the strokes related? So you tried filtering each feature map, you found the edges, you found the strokes in it, and then you tried finding out the relationship between the different features. And hence you captured the style of this. Okay. So now how do we transfer? We have a style, we have information about the style, we have information about the image. How do we transfer this information? Let's get into the maths of it, which we quickly miss when we are, developing apps. So let's get into the math of it. You have a style image. Let's pass it through a VGG16 for now. Okay. You have multiple layers. There are features that you're generating, and you generate style features out of it. AL, which is nothing again but a covariance matrix of these feature maps. Okay. Let's do the same with the content image over here and pass it through a network and get all the feature maps here. Now let's take a noisy white noise image and pass it through the same network. Okay, and then try matching these feature maps together. Let's say, okay, I want to change the pixels in this white noise image in such a way that this image eventually starts looking like the content image. So what I'll do is, okay, you know what? I'll try matching it with the features of this particular content image. So we are trying to find an L2 loss between the features FL and 2L. Okay. Is anyone saying something? So we try finding out the feature loss over here, and now this feature loss can be backpropagated to construct the image. Now there is a problem. Here we use information only about the content image. So essentially when we manipulate this, we'll be creating the content image. Right? I want to create a stylized version of this content image. So I need to find information from this branch as well. Okay. Let's match these features as well. So you have a feature here, you again find out a covariance matrix, and then you try finding out the difference between these covariance matrices. And whatever is the error, you backpropagate that as well and find out a total loss, which is a combination of the content loss that we calculated in the right hand side using the content image and a style loss which we calculate from the left hand side, and we do a linear combination of it. And we backpropagate this loss and we keep manipulating this white noise image until it starts looking like the stylized image. Are there any doubts till now? Like, is this clear? This is what most of the people are implementing. The TensorFlow code, the PyTorch code, Gates et al.'s approach is almost what everyone is working on. So this is what you guys are doing. When you do gradient supply, there's an image, you do gradient supply on it, and then these gradients are applied. And you keep iteratively moving here so that this white noise image converts into a stylized image of that particular content. And you have a total loss, which is alpha times loss of content plus beta times loss of style. Does this make sense?
Harsh, can you give a little bit maybe more later examples of feature maps from left hand side style image and content image on the right hand side?
Sure. So let's go back to the
Harsh, this is Amit here. May I just ask one question here? So one important thing which I noticed is, please correct me if I am wrong. Previously, I was imagining it to be a marriage of two images, but the way you showed it now, I understand that it is actually we are taking a white noise picture and basically trying to get two of them merged into that white noise image, and that is where the final output will be. That is.
Yes. That's absolutely the case. That's a really good observation.
Okay. Thank you.
And coming back to Rahul, your question, feature maps. Well, maybe these are feature maps. So let's say these are two headlights. Here also we have two headlights. These two feature maps will be highly correlated. On the contrary, you will have this new feature map which will not be correlated. So when you will calculate the covariance of this, you will actually find out how different features are related to each other, and that's what your style is. The way the headlights are placed, the design of the car, that's what your style is. Whereas when you are finding the feature maps for this, you will be looking at something very similar to what we look here. The edges, the spokes. So this is most likely. Let me find out a better example. It's clearly visible here. They are capturing the edges and the differences here. Where is the gradient high in the image? Where is the gradient low in the image? And stuff like that. So you're capturing the content from the very initial layers, and you're capturing the abstract style from the final layers. And that's how the feature maps are represented.
And once you have both of them, and then via the mechanisms, various mechanisms you mentioned, one of them coordinates matrix, you are basically trying to sort of adapt it to this right noise.
And that term, yes, and that term adapt is very interesting because adapt is the term that we typically use for meta learning or few shot learning. When we have a learning model and we want to adapt it to a new task, we call it as meta learning. And that's why in my initial slide I mentioned that this is a very strong overlap with meta learning, few shot learning, and so on and so forth. It's very similar. All these things are very, just slight different. Mathematically, they are slightly different, and hence they are different fields. But the big picture idea remains the same. Cool. This is so cool. This worked really well. I was very confused if I'll be able to explain it or not. But that's nice.
First, I have small doubt. I don't know whether you will be. This is Tvarit here. Okay. So I don't know whether you'll be explaining in future or should I wait? I don't know. But on what metric do we calculate? Do we decide that the image which we obtained is a nice image compared to the loss in the previous, compared to the image in the previous layer, the previous iteration?
Oh, you don't really have a way of doing that. I think that's an active area of research. How do we qualitatively and quantitatively measure that a stylized image is actually good or bad?
Yeah. So the loss here is calculating based on what metric? Then?
The loss here is basically how similar are the features from the content and the style. So let's assume that alpha is 0, right? And essentially this part would be gone. You'll just try copying this style, and that is when you obtain something like this image here. Right.
Okay.
But if you say your alpha is high and beta is 0, then essentially you'll be reconstructing this image, which was this example. Certain version of this image. Now you are trying to blend the two, and I'll talk about how playing with alpha can change. Alpha and beta ratio will change the way the images look.
Okay. So generally, to my understanding, in a classification problem, you reduce the loss in order to gain more accuracy, right? Generally.
Yes.
If I'm not wrong. So here, on what basis we are trying to minimize the loss to achieve what? That's what I'm trying to understand.
So we are trying to match the features with theme. So when we have this image, this stylized image, through the same network, the way these were calibrated, we want the features to match the styled image, and we want the features to match the content image as well. We want it to look like the content image, we want it to look like the styled image. Now, to what degree we want it to look like the styled image and the content image is controlled by alpha and beta.
Okay, sir.
And that's how we are minimizing the feature loss of it.
Okay.
Yeah, I understand. If I may add one thing to answer quickly, you can keep track of your N2 loss and also keep track of your correlation or the cosine loss function there. There would be a point of inflection where your losses would stop to reduce, and this is a point which would be very nice for you to stop learning. And another way to actually evaluate, it's just an idea on my observation is, you could have a look at the distance between your content image, your reproduced image, and then again distance between your styled image and your reproduced image. So the average loss could be something that you could take a look to characterize the efficiency of your model.
Yeah,
that's really good idea. That makes sense. You can measure it in some space, like maybe apply KNN or some simple machine learning technique, to measure the distinct image and the content image and the style and this like the original style image and see how much resemblance do we have between the two.
Okay, yeah, I understand. Thank you.
Let's move on. Okay.
I'm Sagar. I have a question here. Hello.
Go ahead.
Yeah. So yeah, this mission is going really good. But I had one doubt in one of the previous slides. Can you go back a few slides back? Yeah, this one. Yeah. I have. Yeah, this one. So I have doubt here. On the top, you have mentioned style representation, and there is the square boxes there. And as you go from left to right, the size of the square box is increasing. So can you tell me, I could not get what does the size matter here? What does the size imply here?
It's the correlation of the features that the number of features are increasing. Earlier they were only layer 1 features, now they are layer 1 plus layer 2 features. Then there are layer 1 and layer 2 features, so slightly bigger size. Then you have 4 layer features and you have 5 layer features.
Bigger termination is we are predicting covariance or in a combination of matrices and it can be eventually same, right?
It depends on the ratio. So essentially these are 3D tensors. These are not 2D matrices. So what's happening is you have an H cross W cross C and you have another H cross W cross dash. Right. So the way you are taking the covariance matters. And hence essentially what will happen is you will start getting matrices which are bigger in size. Because of the different ways in which you will be taking the covariance. Does that make sense?
So can you please repeat that?
I have only 15 minutes left. Can we get back to this after a minute or offline? Because I have to get to the exam and strategy formula for this, and I don't want to complicate it.
Okay, sure.
I'll talk about it in the.
Okay, sure. No problem.
So, okay, we understood the basic, but now what are the factors that affect this particular method? Thirdly, one of them is the alpha beta ratio that we just talked about. Now we have 4 images here, and we are changing the alpha to beta ratio. This image over here in the bottom right corner looks very much like the content image, and here this looks very much like the style image. So it's easy to guess that the beta was high over here and the alpha was high over here. Right, and that's the effect of the ratio of alpha to beta. And precisely, this is alpha by beta's ratio, 10 power minus 4, 10 power minus 3, 10 power minus 2, 10 power minus 1. The second factor is, what image do you start with? We started with a white noise image. Can we start with something else? Obviously, in a classical optimization problem, let's say you have any convex function or any function that you want to optimize, the start point matters a lot. Where would you reach? So, if we not start with a white noise image and we start off with let's say style image or content image, where do we reach? So these are the different variants of different versions of initialization. I wanted to have quiz, but let's just skip it because we don't have a lot of time. The first image here, A1, is initialized from the content image, and that's why if you observe it very closely, it matches the content image a lot as compared to the other images, which were highly abstract in nature, especially this one, like all these buildings, they have lost the edges and everything. Everything is very curved and, just wavy in nature, just like the artist's perception. And these 4 images are different white noise initializations. And that's where I would like to point out that all these outputs are different. And that's why in some of the teams I was mentioning this, that you want to understand what are the parameters that will change your output and how you can actually come up with algorithms which are robust to it, or at least give the user the choice, what kind of output you want. Okay, now we had the 4th layer as a feature loss and a 5th layer as a style loss, right? And maybe some other layers as style loss, a weighted combination of it. But how would this change the stylized image that is produced. Well, let's say this is your content image and this is your style image here. Can you guess which features were used for producing this particular style image and this particular style image? Like you have here edges over here, which gives me a hint that okay, maybe the feature loss over here is the initial layers because it's high level features and it's very wavy and abstract, so maybe it's some high level features used over here. So low level features used here for content loss and high level features used here. And conf22 was used here, which is like the second layer features, and conf4 features were used here. Cool. Now, transforming a white noise image into another image using iterator process. Well, can we use neural networks for that? That's the next paper. And that's the problem with this particular paper. You need a lot of iterations and it's very slow. So can we do real-time style transfer using neural networks? The next paper by Fifi's group, Justin Johnson, they propose, if you look at these two diagrams are actually very similar, it's just a different way of representing it. You have an input image, you have a styled image, you have a target style, you have a target content, and again you're using a G60 and style feature loss at different layers, content feature loss at a different layer, and combining all these to make the stylized input. The only difference is here you're using a neural network instead of a white noise image transformed iteratively using LBMHs. So the loss here was the feature loss, the style loss. You can consider this as alpha, the beta is the way we did. And they have a total variational loss as well, which a lot of you might have read in the blogs that you were reading. I noticed that the TensorBoard blogs and the other collab notebooks had this term, total variational loss, TVL loss. Now what is a TVL loss? TVL loss is nothing but a denoising loss. It's a regularizer. So when you apply TVL on, let's say, a noisy grainy image, it becomes smooth. That's pretty much the effect of TVL. And that's why it is often used as a regularizer in most image processing problems. So yeah, here are some of the results of that. You have a style image, the Starry Night, which is number, and style image, the Muse, and you've converted these very normal, ordinary images into amazing stylized images. I'm pretty sure you must have fiddled around with these images and these styles as you were working on your problem statement, right? These are very common styles that our typical neural networks are trained for. Okay, what next? So that's a typical way in which mostly problems, move in machine learning. You first have a very simple iterative algorithm. Then you have inputs, and then everyone wants to move towards unsupervised learning, so GANs. Right. So here are some of the results people referred to as unpaired image-to-image translation using site-consistent adversarial networks by Julian Zhang. Amazing person, an amazing perception of things, but cool. Let's move on and see what he did. But let's first cover what is a GAN essentially. I'll just do a very quick high-level picture here. And it's already for 85 more minutes. So, GANs refer to a broad class of generator model problems where essentially you are playing an adversarial game between a generator and a discriminator. You have two neural networks. One is a generator, the other is a discriminator. Right? And they are playing an adversarial game. Let's take an example. This is a classic example that's used for explaining GAN. There's a thief and there's a police. The thief is trying to make fake notes, and the police is trying to identify which note is fake and which note is real. So the thief comes up with a box with written 100 on it. The police clearly says that okay, you know what, this is fake. It's not even green. It's giving it a signal. So now he understood that okay, you know what, I need to make it at least green. So he makes it green. He says there is no watermark. He adds a watermark. The watermark should be rounded. And hence, slowly and steadily, iteratively, your generator learns how to fool the discriminator. And will start producing notes, the thief will start producing notes when the police cannot really identify it, if it's real or fake. That's the typical game. you are having an adversarial game between two neural networks where one of them is trying to fool the other. Now, how do we use that in this particular setup? You have this set of images where, let's say, one is sketches and other one is images. There is one very significant problem with supervisor, and that is you need very large data sets, and you cannot really capture all sorts of abstractions here. Like, let's say a human will annotate it, so you might use scanning edge, maybe you will manually sketch it. But there will be only certain aspects that a human can capture, because you cannot really put it on paper. But this is what I'm trying to capture, and you need extremely large data sets for it. Let's have an unpaired set of images. Let's have some n images where n are like photorealistic images, and y domain y, which is basically a set of paintings. Okay. Now let's move from x to y by training a generator which takes an image as an input and generates a painting. And then you have a discriminator that tries to identify whether it's a painting or it's an image. Okay. You also train another neural network which moves from painting to an image, and then you have a discriminator over here which says, okay, you know what, is it an image or a painting? So dx and dy. Dx is trying to understand whether you are in the domain x. Dy is trying to understand whether you are in the domain y. There is one significant problem with this setup. Now let's say I enter this particular painting and I get this particular photo and I get a painting which is of a forest. I don't want that. I want it to match this content. Hence, cycle consistency or basically conditioning of your neural network. What I'll do is, I convert the x into a y, and then I pass that predicted y back to f to generate the x. So let's say I had an image of a fort. I try to generate the image of a painting, and then I try to generate a painting of that particular image, and then I move from that painting of that particular image back to the image, and this should exactly match, and hence cycle consistency comes into the picture. And you can have another similar setup where you move from painting to an image and you can apply cycle consistency there. And this is what is referred to as a cycle gap. This is a really powerful idea. It's a very simple idea, but it's a really powerful idea. Essentially, we are trying to condition not based on the input, not based on the labels, but the neural network itself learns to condition. And that's what the beauty of this very simplistic method is. Although this paper is really complicated, but it's still the high level picture. And that's what, this paper changed the game of stylization essentially. You can see the results, they are pretty amazing. Also, this was not only used for paintings and stylization, this was also used for generating depth maps, Google Maps, feature maps. I remember someone showing me, depth networks being used. Like, let's say you have a face and you want to make a 3D model of this face. You can use this for that as well. And the GitHub repository refers to as pix2pix. Not pix2pix, sorry. Pix2pix using cycle gaps. Pix2pix and cycle gaps, something like that. I'll share the link with you. And the way to use this code is really simple. I just have 2 folders of images and you pass that and it works. It's amazingly simple and it's a beautiful idea. Hence, we covered basics about who I am and what is it, and we understood the big picture of neural style transfer. We also understood how classical methods were used, and this is not exactly a problem, but DL has changed the scope of this problem. We talked about some prerequisites, and we went on through 3 major papers, just to mention, which were image style transfer using convolutional neural networks by Geekus et al., which almost everyone's familiar with, perceptual losses for real-time style transfer and super resolution by Tvarit, and unpaired image generation using cycle consistent adversarial networks by G60. That's it from my end. That's the presentation. Any questions, any doubts we can have now, we can have it in the session, we can have it offline in the hackathon, whatever it is. Thank you.
So anyone with their queries or doubts, anything that they want to clear right now? I guess no one.
were people able to follow? I'm more interested in that. Was it clear? Was there something that it could?
That it was really perfect and it was really illustrative. We conveyed the topic in the best way, I would say.
Yeah, really, Harsh. I mean, thank you very much. Thank you very much for the explanation and the way you have explained the subject. I would say you have touched the most unexplained query also of the members over here. They might be having certain things or doubts in their mind, but without letting them know, you actually cleared everything. So your explanation was very nice. Thank you so much for giving glimpse on this subject.
Yeah, just to make help everyone that whatever we are presenting, it will be shared on the general Teams channel itself, the content, so that you can also refer. So Harsh, from your side, it will be yeah.
Yes. So I will first present the points. Maybe if any of the mentors have any other points that we can add, then we can definitely add. So the first evaluation criteria is the number of challenges completed. So we had 3 challenges. First one was neural style transfer. The method itself. The second one was the web application development, and the third one was deployment. So based on the number of challenges completed by each team, the points will be given here. And the second criteria is the style, is to evaluate the style transfer. As Harsh mentioned, there is no quantitative measure that we can use to say whether the style transfer is perfect or not. So based on this, we also I refer to the research paper that Harsh has mentioned. So in based on the points that were discussed in the research paper, I came up with these two. So one of them is the loss comparison. That means we are going to run the neural style transfer for 500 iterations, and we are going to start with a content image if possible. And the deliverable is the let me show you the images first. So we have 4 content images and 4 style images. You can run the style algorithm for 4 times. That is style 1 with content 1 and content 2 with style 2, etc. So you have 4 different iterations here, 4 different outputs. So you will need to present the loss arrays as a CSV file, which will have the team name as a start, and then the image number, and it will be in a CSV format. And those losses should contain the total loss, style loss, and the content loss separately if possible. And the other deliverable is the output images itself of these 4 iterations. And for the web application, the functionality of the UI will be considered. Whether you have an upload option, how are you displaying the images, etc. will be considered. And for the cloud deployment, you will be awarded extra points. Like the cloud deployment itself is a bonus for you, and also you will get extra points for if you have used a Lambda function to deploy it. So these are the evaluation criteria. If the experts have any suggestions or changes that I can do, we can write with me.
This is Sachin here. Maybe let's take a call later. I have some suggestions. Let's discuss it together with Rahul and maybe Harsh also.
Yeah.
And then maybe we can update everyone regarding it.
Okay. Yeah. Sounds good. Okay. So we will update this, and these will be the main points as far as I understand, and probably 1 or 2 points will be added or modified. So based on that, we will post this in the general channel, and now I would suggest all the teams to get started.
Yeah. So everyone please focus on the cloning part and also try to run the iterations on the image shared by Pranay. The exact evolution criteria we will also discuss once again, and then we will put it in the general chat functionality so that everyone can also see again. Yeah.
I will right away share the images. I have the zip file here. So
So any questions from any team? Anything technical, non-technical, organizational, demo-wise? Feel free to ask. Otherwise, I think we can wrap up this section and yeah, we can go back.